Hello, and welcome to the CPM webinar series. Today's topic is why extruders need a torque limiting coupling. My name is Christian Davis, and I will be your moderator for today's event. With locations around the world, CPM is a leading global supplier of twin screw extruders, extrusion systems, high performance replacement parts, ring extruders, thermal equipment, and supporting services. Our webinars are intended to service, support, and inform you about the latest technologies, maintenance methods, and trends in the industry. Presenting today's webinar is Karl Tietz. Karl has more than a decade of experience in extrusion industry, from building to designing and manufacturing. As CPM's Global Extrusion Systems Director, Karl works closely with our customers to support mechanical, electrical, and process needs, among many other responsibilities. If you have any questions during the webinar, please type them in the questions field. If it's not answered, you will receive a follow-up response by email. Karl, I'll now turn it over to you.
Thank you, Christian. Good morning, everybody. Thank you for joining our webinar, and we'll jump right into this. I just want to say first of all, some of the terminology we'll use here today is common language within CPM. It might be different outside of CPM, but it gets down to the same fundamentals. So why does an extruder need a torque limiting coupling? Let's answer that question. It's a pretty easy question. It's to protect your extruder from a catastrophic failure. So we'll get into why extruders see catastrophic failures and how we try to prevent that with a torque limiter, and we'll talk a little bit about different torque limiters, how that torque limit is calculated, and then just a few things around why your torque limiter disengages and what to look for. So first of all, motors are really it's a really dumb power transmitting device. It's not intelligent. It doesn't know. A motor only reacts to what it sees, an electric motor. And you can see the current draw of as an equivalent, a current draw of an electric motor as the equivalent of a gas motor, gas for an internal combustion motor. So it just really reacts, and the motor just reacts to the load it sees. That being said, you can electrically protect the motor. And how is that done usually? Usually you can do it with a direct online driven motors use breakers that trip at an overload condition with too much current. But VFD driven motors, which are usually used on extruders, can be torque limited by the VFD and a control system. The disadvantage of the electrical protection is a really slow response and an instantaneous overload. So if you have a quick overload on the machine, and modern torque limiting couplings allow for that instantaneous disengagement of the motor from the load to protect the gearbox, the shafts, and hopefully prevent a complete catastrophic failure. So just a little bit on typical motor, extruder motor characteristics. VFD motors are designed to transmit a constant torque up to a specific minimum speed. So they've got a speed range in which they can deliver a constant full torque capability of that motor. This speed is usually given on the nameplate as a ratio of turn down. They call it a turn down ratio. It could be 4-to-1, 10-to-1, 1,000-to-1. What this means is there's a thermal equilibrium that the motor can maintain at a maximum torque level with this low speed without damaging the motor. If you run the motor at the maximum torque rate below this speed, then there's a big thermal increase on the winding temperatures, and that degrades the insulation and usually can damage a motor. So for an extruder motor, you want to stay within that turn down ratio, and this can be anything from 10-to-1 to 1,000-to-1 that we've seen in the industry out there. So a few overload examples. Twin screw extruders are normally star-fed machines, and what this means is you can control the load on the machine with different feed rates, with screw speed of the motor, and different raw materials you run. This allows you to run near 100% at various speeds, and you can control that torque you're using on the machine very well. Running near the 100% torque requires protection against sudden overloads that can be created by foreign objects like bolts or springs or something that come into the extruder and cause a blockage. Feeding surges usually can cause that by bridging and hoppers, or a feeder overfeeds for a moment if they've lost some weight and somebody touches it. And if you run close to that 100% torque limit, it's really easy to trigger that overload condition. The other one is an operator error. If they incorrectly enter a feed rate or they increase the speed too much at a time, the machine exerts a lot of power, and then just this, it overloads, and you'll need a disengagement method there. The different types of torque limiters that can be utilized on the extruder are shear pin torque couplings. We've got friction slip couplings. We've got ball and plate style disengagement couplings, a modular ball detent style coupling, and pneumatic torque limiters. We'll go through each one of these to just give you a little bit of an example. These are not. We'll show the ones. We'll go a little bit more in detail on the ones that are most commonly used. These are not always commonly used on extruders, but we've run into them out there in the industry, and we've seen them on various machines. So let's get into the first one. The shear pin coupling uses shear pins. The disengagement levels are usually set by the pins that shear right off. And as you can see here, it's just pins that are in a circular motion around the torque limiter between the motor and the gearbox. What's the advantage of this torque limiter? It's really economically, and it's got really low maintenance. The disadvantages of these torque limiters, or this torque limiting device, is the shear pins need to be replaced after an overload condition because it rips them all off. The disengagement torque is usually influenced by cyclical loading. So if the machine sees, overload close to overload conditions and less load conditions, it really influences the material of that shear pin, and that creates a variation in the accuracy due to that difference in loading over time. This is a time constraint. Also, there's a variance in accuracy depending on what material you use for those shear pins. So the accuracy is not always there on these torque limiters. Then we get into the friction clutches. A friction clutch disengages. The disengagement levels are set by a preload of the pressure plates between on top onto each other. The advantages of this one is it's also an economical advantage, but it's got quite a bit of disadvantages. It's got extensive maintenance on the wear parts if you have a regular overload condition, and usually if you overload them too much with one overload, you have to rebuild the whole torque limiter. The load is not completely removed from your drivetrain, so from the gearbox, you always the downstream always sees some load and still can cause damage. So it's not a complete disengagement. And then when the friction clutches slip, it creates a bunch of heat that's got to be absorbed or conducted into the motor and the gearbox, which could be just a small amount, or it could be a lot and damage the bearings on the input shaft and on the motor shaft. So that it's just, there are better ways of doing it. Then you get into the plate and ball couplings. This disengagement level is set by a preload of the spring on the balls and the pockets. As you can see here, you've got the spring that pushes on the plate that keeps the balls in their pocket. And in an overload condition, those balls pop out, and the back half spins by itself, and the front half and the other half is stationary. So the set of balls actually are actually loaded into the pocket of the spring, as mentioned, and when it disengages, they pop out and they rotate. During the overload condition, the balls completely move out of the pocket, but they still spin on the stationary half, so you've not a complete 100% disengagement there. And if the control system doesn't pick it up fast enough, those balls also generate some heat and could damage the torque limiter a bit. So they also have a disadvantage in that area. Re-engaging these torque limiters is pretty easy. You rotate the two halves counterclockwise from the operating direction, and the balls usually pop back into space, into their pockets, and it's re-engaged. The next one we're going to get into is a modular ball detent style coupling. These are probably the most common torque limiters on extruders. The disengagement levels are usually set by a combination of the following: the number of modules on the torque limiter and the adjustment of the spring on that module itself. During an overload condition, it's very similar to the previous torque limiter. The ball pops out of the pocket. But what happens here is when it pops out, it goes onto the side where it disengages completely from the other half, and the torque limiter is completely disengaged and spins freely. Resetting is really done easily. They've usually got a line on both sides of the torque limiter. You align the two lines and you pop back the modules, and it's ready to go. So it's really easy, and the wear on these torque limiters are really minimal. They're widely used. They're very, very accurate. One torque limiter usually covers a big range of torque that you can disengage with, and they're very accurate over multiple disengagements. It completely disengages, and their maintenance is fairly low. Also, what makes these torque limiters really good or really easy to use is when you have to replace one, you can just loosen the hubs on each side. The center section falls out, and you can just pop in a brand new center section and bolt it up, and you can go. It doesn't need motor realigning or any of that. So it's really an easy torque limiter to maintain and use. I've got a little video on this torque limiter to show you how it disengages. So it'll rotate, and if you pay attention on the modules, it just pops out and the one half spins free. So once those pop out, you can easily see it's disengaged as well. With the others, it's really hard to just know that it's disengaged. Then just a little bit more on how it works. On the left-hand side, you've got the pocket with the ball in it, and on the right-hand side, you've got the module. And when it disengages, that ball pops into the module, and the two halves can spin freely, as you see here. Next, we are going to look at the pneumatic friction plate clutch. These we see in the industry quite a bit as well. Their disengagement level works a little bit different from just the normal friction plate. These work with a combination of the friction on the two plates and air pressure that pushes the two plates together. So these torque limiters also can go into a variety of ranges due to the adjustment of the pressure. They are actively controlled torque limiters. So a control system activates the air, and you can control when it's engaged and completely disengaged. It does, when you disengage them, it does completely separate the two friction plates. So you have the same as with the modular torque limiter, where it's completely free from each other and can rotate on one side, and the other side is completely on its own. How these usually work is they need a little bit of slip first before they disengage. So the control system looks at both sides of the torque limiter on the speed, and if one is slower than the other one, then it removes the air pressure to disengage it. But for that to happen, the torque limiter needs to slip first, and some people use that more as to try and save the machine from overloading, and they use it as an advantage. In some cases, we've seen that it's really a disadvantage, because it's the same with the friction plate clutch. It keeps that overload torque on the machine going until that air pressure is removed. So you're between a rock and a hard place on that end if it comes to disengaging and it slips. Same with these as with the friction plates, is if this one slips too much, then the whole torque limiter needs to be removed and rebuilt. It's not like the module, the ball and detent style, where you can just re-engage it. If there's too much friction between the two plates, you have to redo the torque limiter because it loses accuracy over time. So here are some of the advantages. It's widely used in the industry. They are really repeatable if they don't slip too much, and they cover a big range as well. They are fairly expensive as a disadvantage to put them on, and they need air through the through the shaft of the gearbox, and not a lot of OEMs build their gearboxes with holes through the shaft to do it on. So it limits you to which gearboxes you can put on your machine. And if it slips too much, you have the same heating problem that you have with the friction clutches. So now that we looked at all the different torque limiters, we're going to look at how a torque setting is calculated. Different OEMs calculate the specific level differently. At CPM, we put the torque limit at 110% of the motor power, and I'll show you how we calculate it. So usually you calculate the maximum torque of the motor that the motor can transmit by using the shaft power, the ratio of your gearbox, and the base speed of the motor. In some cases, extruders have bigger motors on them that they can use on the gearbox and the shafts, and that's not due to a lack of providing a good combination. It's just you are stuck with the motors that are out there, and you gotta use whatever motor is there. And if you want to use the full potential of the machine, sometimes you need to put on a bigger motor and just current limit it with the VFD to bring it down. And in the case where the motor is sized correctly or sized appropriately for the combination of the gearbox and the shafts, you use that maximum permissible torque of the motor, and you make sure that the gearbox and the screw shafts capability is above that. And then the disengagement torque can be calculated by using the maximum torque calculation shown above and multiplying it by 1.1. This puts you at a nominal torque of 110%. In the case where the motor is too big, or is bigger than what the combination of the gearbox and the screw shafts allow, in that case, you current limit the VFD to the maximum power, to the maximum torque delivery that the gearbox and screw shafts can take. And at that point, you use the same formulation as shown in the previous slide, and you still multiply by 1.1 and get your disengagement torque. So it all comes down to the combination of the gearbox and the motor and the shafts and what the different torque levels are. Typical maintenance on different torque limiters or on these different types, we always refer customers to the OEM manuals to make sure that they are properly maintained and in intervals maintained as prescribed by the OEM manufacturers of the torque limiters, and it can vary. Typically, the moving parts need some kind of lubrication. For instance, grease is probably the most common one. The one thing that is really important to note is that the rotating parts and the module parts usually use different kind of greases. So it depends on the torque limiter, depends on the brand, depends on how the OEM set it up. It's really important to note that it might not use the same grease or the same lubricant on all the different components in a torque limiter. We've seen it being done where customers use a specific grease on everything, and then the torque limiter doesn't work properly after a certain amount of time, and it creates disengagement problems. The flexible connections usually have a lifetime as well, and they need some replacement after some period of time. Again, the OEM will recommend that in their manual. The pneumatic torque limiters might have some air system components that need maintenance. And again, if the air pressure varies on those torque limiters, your accuracy and disengagement is influenced and can cause trouble. Typically, couplings should be inspected annually at least to make sure they are functioning properly and protecting your machine as designed. And then if any disassembly is needed or maintenance is needed, it's really important to have trained personnel do it. due to the impact of it being done incorrectly, and the torque is changed, that disengagement limit is changed, it creates a lot of it can create a lot of problems for your machine and damage. So what happens? Why do torque limiters usually disengage during an operation? Um, there's usually a sign. If it does disengage during an operation, it really is a sign of a potential serious damage of the equipment. So it's really important not to just re-engage it and try again. Um, it has to be investigated, and if it comes down to that, it just, it's a small thing, that's fine. Re-engage it and run it. But there's a reason for the torque limiter. There's a reason it disengages, and it's usually to protect your machine. So just, re-engaging it and going again a is a really, really big risk you run. Usually, where you start off looking for is you look for buildup of accumulation in feed hoppers and side feeders. So it's just a feeding overload. In that case, you can just re-engage it and make sure the machine is heated up enough and clear it out and start again. It's important to review trends that are displayed, the percentage of torque, the feed statistics, the speed of the machine. So just looking at what the machine control system tells you, identifying potential foreign objects that could have gone into the machine. That's also one that's really a big influence on torque limiters disengaging and protecting the machine. And usually, if they get something in, something breaks internally as well, that lodges the two together. So it's really good to open up the machine and make sure that there's not more pieces in there than what you expect. But the most common one is usually feeding upset during an operation. So one of the other things we see a lot is if torque limiters disengage on a startup. So if a torque limiter disengages on a startup, the first thing we always look at is, was the machine cleaned out and screw shafts installed previously to the startup? If that's the case, there's a really potential of a mechanical problem on the screw shafts or screw elements being stacked incorrectly, and which causes the machine to hang up and disengage the torque limiter. And the easiest way of checking this is just by rotating the torque limiter by hand when the machine is completely locked out, electronically and electrically, to protect the operators or the maintenance personnel. And just see if you can rotate it by hand, the amount of times the ratio of the gearbox allows for a full rotation. If it turns properly and there's no sticking point, then the shafts are good. If there is, the shafts have to come out, and the incorrect stacking has to be found. The other one is the machine needs to have a sufficient heat soak time. So the resin from the previous run is still in there, and you just need for it to be all melted before the machine can start up. And then the other one again is look inside the side feed hoppers or in the main feed hopper. Sometimes side feeders energize at 50 RPM automatically, and if there's material in there, it pushes it in, and without your main resin or your main feeding product in there, whatever's in the side feeder goes into the extruder and binds it up, and it disengages the torque limiter. For instance, minerals or glass fiber, I'm pretty sure a lot of people out there have quite a bit of experience with running polymer without polymer, and these things get into the machine and locking them up. And then it just solidifies the machine and disengages the torque limiter. And then one of the other scenarios we run into a lot is customers call us and say, my torque limiter keeps on disengaging, but the machine is only running at an X percentage, say 75% or 80% torque. One of the reasons that the torque limiter is used is to protect the machine from overloading where the electronic system cannot be fast enough to catch it. So there might be something that you can't see on the trends, or a feeder that spikes very quickly. If that overload condition occurs really fast. A lot of the control systems don't sample enough information to show that. It just shows an increasing trend, and the machine does really over torque. In other cases, it does prematurely disengage. We've seen quite a bit of that as well. And how to test that for premature disengagement is you run your machine at about 50% of the speed, and then you gradually increase just the polymer really slowly to increase the load on the machine until you get to that point where it disengages. And if it prematurely disengages, then it needs either maintenance, it needs an inspection, or the torque limiter is just not set up right. So there's various reasons for it, and it needs to be inspected, but you can test for prematurely disengagement. So a summary of the torque limiter presentation today. We use torque limiters to protect our machines from fast transient load conditions that electronic shutdowns or protection cannot prevent. We usually try to stick with couplings that disengage completely from the motor and the gearbox to minimize wear and damage to the machine. If torque limiters do disengage, it should be thoroughly investigated before restarting the machine and making sure everything works properly. And if they do disengage frequently, they should be checked. Settings should be tested, and maintenance should be done on the torque limiter. Any questions?
Thank you, Karl. There was one earlier in the presentation that said, what about steel types used in barrels? Will this be considered?
Sorry, can you just read it again, Christian?
Sure. What about steel types used in barrels? Will this be considered? And this was early on in the presentation, if that helps for.
So if by that question is mentioned that the material type of the barrels, the liners, this is not a consideration it's consideration on what the disengagement torque is, just due to the torque is not exerted on the barrel itself, so it doesn't have any influence on the integrity of the barrel.
All right. Well, thank you, Karl, and everyone who joined us. A recording of this webinar will be available on 1cpm.com within the next week or two, where you can find all of our previous editions as well. This concludes today's webinar. If you have any more questions or would like information on what CPM can do for you, please email us at extrusion.sales@cpm.net. Thank you.